Good afternoon, everyone. Thanks for joining us today for Rethink Additive Manufacturing with PolyPropylene. My name's Diane Travato, and I'm part of the marketing team here at Prodways. Just a few housekeeping items before we begin today's webinar. All participants are in listen-only mode, and your microphone will be muted, but we do encourage your questions. Please submit any questions by typing them into the lower right-hand corner of the toolbox panel, and we'll do our best to answer them during the Q&A session at the end. The slides for today's webinar are available for download in the handout section on your control panel. You will be receiving a follow-up email with a link to today's recording. Okay, let's get started. It gives me great pleasure to introduce our panelists for today. We've got Lee Barbius. Lee is our regional sales manager here at Prodways. Jeremy Voss, he's our business development manager for BASF. And Dave Hockemeyer. Dave's the owner and co-founder of Peridot, which is a full-service product development company in Indiana. He's a mechanical engineer with over 20 years experience operating and applying various types of 3D printing technologies in an array of applications. He's an early adopter of PP 1200, and he understands both its effectiveness and its limitations. Our agenda for today's webinar includes Lee and Jeremy are going to take us through an overview of polypropylene, its features and major benefits to your business. And then Dave is going to take us through some utilization cases for PP 1200 from prototyping to functional parts and how it has helped him increase market share at Peridot. Now I'd like to hand it over to Lee to kick us off today. Lee?
Thanks, Diane. I'm Lee Barbius. I'm the regional sales manager here for Prodways. And as Diane mentioned, today we'll be discussing different ways that PP can change or enhance your business through additive manufacturing. Now, before we jump into this, I just wanted to do a brief overview of who we are at Prodways and what we can offer. So Prodways, we are a 3D printing and digital manufacturing solution provider with our world headquarters in France. But we also have a US location here in New Hampshire, just north of Boston. Our 3D printers really fall into three categories for us. We have our wax drop-on-demand technology, which is through the SolidScape brand, which is mostly focused on the jewelry industry. We have our Moving Light DLP series printer, which is a resin-based machine heavily focused into the dental world. And then we have what is important to today's discussion, our P series SLS machines. So that's a brief overview of who we are. But before we jump into our discussion today, we wanted to put up a quick poll to get a better understanding of how your business is running today and what your thoughts are and where you're going forward from here. So Diane, if you wouldn't mind throwing up that poll for us real quick, we'll give you guys a minute to respond to that.
Our question is, have you considered transitioning into an injection molding component to additive?
So since we can't organize, the panelists can't vote, I guess this is a good opportunity to to chat. Looking forward to your responses from everybody that's in attendance today. We're going to highlight this as polypropylene specifically as a way that you can do this, where you can actually transition. And Dave's going to talk about this. It's a pretty exciting piece of the puzzle here, and one of the big things that makes polypropylene really unique. So please take the opportunity. Let us know how that lays out, and we'll be eager to answer your questions later on as well.
Excellent. So I guess that's why we're having this this presentation today. A lot of you are interested in learning about how you can move an injected molded component to the additive world. So I guess we'll jump right into it a little bit here. Diane, if you could maybe jump ahead a little bit. I think it's important to first state why we felt it was important to dedicate a full webinar to one material. As we've said before, polypropylene is the most commonly used polymer in the world. And because of its versatility, it is used in a wide variety of applications. We will touch on some of the applications and let Dave do a deep dive into a couple of them. Jeremy and I are going to walk you through some of the features and benefits of running the PP1200. But if anything is unclear and you would like further explanation, please drop us a question in the chat and we'll be happy to circle back to them at the end. So the first benefit that we wanted to, or the first feature that we wanted to highlight here is the chemical resistant nature of polypropylene, which makes it excellent for use in automotive applications and really opens up opportunities for broad media contact. So I mean, if you're able to run a wide variety of liquids and fluids through the material. The next one that we want to highlight here is the strength of the material. So with a very high burst pressure, it enables flexible parts, which is great for living hinges or snap fit parts, but it is also great for shock absorption applications. So what we see there a lot of times, actually recently we've seen a lot of interest in the orthotics world, talking shock absorption. We've seen a big interest in it for that application. And then the next one here on this slide that we wanted to highlight was the cost effectiveness. And this is something that we are going to come back to over and over today. I'm sure you'll get sick of hearing it, but it is a huge benefit. To a lot of you, it may be the most important benefit. You're all here to learn about a new material and how you can enhance your current business. But at the end of the day, that means putting money in your pocket. So there is no need for a material substitution in a lot of these applications because polypropylene is already so widely used throughout a wide range of applications. Another important factor here is the low cost per part. PP is a lot cheaper than comparable materials. It has a better refresh rate, and it has the overall cost is cheaper.
Yeah, Lee, one thing to kind of pull in here is just to kind of talk about how these three things are really the drivers that we see in a lot of the industry projects in additive manufacturing, and these are the drivers too that are going to open up some real opportunities in additive that we don't see right now that are just not traditionally thought of in additive because of this unique combination of properties, right? So we've got materials out there that have chemical resistance and strength, but combining that with the cost-effective nature of polypropylene is a really unique combination. And Dave's going to hit on this a lot as we get into the applications as well. That these three things really pulled through for those applications for Peridot. And it's something that we want to put out there and encourage and have you as the attendees today think about how that plays into your unique applications.
Excellent. So Diane, if you wouldn't mind switching over to the next slide here, we'll jump into this a little more. So we have obviously there's a lot of features and benefits here. So we'll run through this. Jeremy, I'll drop a couple lines here. If there's anything you want to add on to each one, feel free to jump in at any point. So we'll kind of just run through these quickly. So the sustainability, because of the refresh rates and, less waste, the material is, what you could consider to be, a green material. Jeremy, I don't know if you have anything you want to add on that one.
No, that's probably one of the key ones to bring up is the idea of sustainability. Refresh rates in the machine are extremely low or high, right, depending on how you want to look at it. But we'll get into this as well. But we're looking at a 30% new material per build, so 70% used material in each build. And even with that, I think Dave's seen a lot longer use probably than what even we thought on being able to reuse the material. The recyclability as far as the machine goes is very, very high.
Right, and then guys, I would add too for our audience, manufacturer specification, yes, 70-30 ratio. And of course, as a processor, you always push the envelope a little bit. Have we gone a bit beyond that? We sure have. And this material does seem very robust. It's flexible in that way. You want to push that envelope. There is some effect on color and some properties, but that 70-30 ratio has proved to be very robust, very bulletproof to put out good parts.
Excellent. So the next one we'll jump into is the weldability. So I know this is something Dave is going to touch on when he gets into his portion of the the presentation. But this makes the material great for tanks, reservoirs, tubes, pipes, you name it. It also enables you to create larger parts that may not fit inside a typical build chamber and need to be assembled afterwards. It allows you to assemble these parts with injection molded parts as well.
Yeah, I would just add to that. There's kind of this two-prong approach with this, right? Because you have this unique ability to have the material act like a traditionally manufactured material when you weld it, and we've not had a welding or even a staking or fastening operation that's used in traditional polypropylene that hasn't worked in the printed polypropylene. So that's been really neat what we've been able to see. But one of the most interesting use cases, this is a little bit outside of what Dave's going to talk about today, but has been a manufacturer that actually wanted to be able to prove out both do prototyping for a part, but then also prove out the manufacturing process at the same time, right? So you've got this interesting ability to print fittings and affix fittings to a manufactured bottle, and you've got the ability to print fittings right onto the bottle, and then you've also got the ability to add fittings onto a printed bottle, add manufactured fittings onto a printed bottle. So you've got all this flexibility that comes from the ability to weld this material, and it just opens up a lot of potential that we haven't seen before in additive.
So we'll keep it moving with the low density. We're looking at parts with the density of 890 kilograms per meter cubed. Which enables lighter parts, and again, touching back on the cost savings. I told you we're going to mention this a bunch of times. It allows you to fill your machine with less material. So I don't know if Jeremy, anything you want to add to that?
Yeah, it comes back to that big picture sustainability idea, both environmental and sustainability for the end user.
So we'll talk about high recyclability. Again, this is another thing we're going to touch on quite a few times. But as Dave and both Jeremy mentioned earlier, has a refresh rate of 30 to 40%, meaning that with each new build, you're only adding 30% of new powder. So this is much better than the typical SLS powders on the market, and again points back to the cost savings that you can achieve using this material. It also enables your sustainability programs and allows you to reduce waste within your 3D printing programs. We'll jump to so high HTT. So PP1200 has an HTT of 102 degrees Celsius, which enables a broad range of production application and really opens up new fields of demanding environments. So it opens up, high temp applications. Jeremy, is there anything you want to add to that?
Well, and that also is going to carry us into a couple of these other ones, right? So so that high HDT opens up applications. Dave's going to talk about that. No water uptake also opens up a lot of applications for us, as well as the chemical compatibility and the media tightness. All of those things are things that are going to open up those new applications for us. And maybe the last one, Lee, to kind of circle around is this idea of known material. So what we're seeing is that this is a very readily accepted material because it's so widely known. Lee, you started out saying that at the beginning, right? This is polypropylene's the most widely used polymer around, and that really is kind of what brings it all back in here for this conversation, is the idea that it's easily accepted, even if it's not maybe what you started out with for additive. It's people know the material, they know what to expect, and so it's been a really easy, easily accepted material as we've gone on to launch this. So it's kind of circle up on all of those things. And I would imagine there's probably a couple people out there that are like, can we see the TDS?
Right, and as we transition to the TDS, I would add to that, Jeremy, that in the prototype arena, again, we'll talk about using this technology for production also, but it's very refreshing as a prototype provider to say, this is polypropylene. And as simple as that sentence is, it's the real material, as opposed to prototyping in the photopolymer arena. Well, it's like nylon, it's like ABS. No, this is true polypropylene, and that's been very rewarding and very wonderfully accepted by the engineering and product development community, that it's true polypro. It's
right.
Not a simulation.
Yeah, that's cool.
Yeah, and just to add to what Jeremy was saying too, with it, it's obviously a known material. So adoption by your customers, should be very comfortable with adopting this material. But it is also a relatively new material to the additive world. We've had it in our portfolio here at Prodways for a little over a year now. So the market is still a little green, but it's a great opportunity to be an early adopter, as Dave has been, and he'll be able to speak a little bit more about how it's really changed his business. So I guess we can't just skip over some of this. We'll jump over to the TDS. We'll throw that up there. So Diane, will you next slide, please? So on this slide, we won't talk through all of these specs one by one. I think we might put a few of you to sleep. But there are a couple things that I wanted to point out when looking at PP as a suitable replacement for PA12. So PP is 10% lighter than PA12 for one. So back to that cost effectiveness of the polypropylene. It carries a 25% lower price with a better refresh rate. So I'd be happy to, one thing I'll throw out there, after this, if anybody is interested in seeing simulations or anything, I'd be happy to run the cost analysis for you to show you the benefits. Jeremy, is there anything you want to point out on this slide here?
I think we've touched on the broad strokes here. Those that are interested in the TDS can see it here, and obviously it's in the handout too. So all these slides are available, and full information too is available on the Prodways website. One of the things that that I just thought of as we're talking about this is that BASF has recently launched this material in coordination with the Shapeways platform that you can order this, you can order parts in this material directly from shapeways.com. So you can go on Shapeways and enter, upload your part file and have it within a week or two based on that platform. So would encourage you, if you want to start exploring this material, and we can bring that up again, but would definitely encourage you to visit shapeways.com. You'll see the BASF logo on the bottom left-hand corner. Just click through there, and you'll be able to get parts printed quickly and be able to start exploring the material.
Good point. Good point. So I guess at this point we'll turn it over to Dave. Dave's the star of the show. He can show you how he uses this in real life applications.
Finally, we get to the good part.
Yeah. So Dave, if you wouldn't mind, we'll hand it over to you and let you do your thing.
Thanks, guys. Way to add the pressure. Appreciate that. So as we get started, audience, we're going to have two applications here, two of many that we've been able to explore, but we've chosen two here because they both show, especially this first one, shows many aspects of the positive characteristics of the polypro material. So what you're looking at here is a housing. It's a housing. The application for this is in the aerospace industry. The environment of this is going to be outdoors. Obviously, there's limited information that I can provide from an application standpoint, but you're looking at a housing design. And the first thing that you may pick up on is it's kind of a half of a cylinder. And I have the parts here in front of me, but I'm going to try real hard not to hold stuff up to the camera. But the first feature we're taking advantage of on this material is the ability to print live hinges. So that's what you're seeing in the middle of this housing design, that thin-walled section. We print it as is. There's some tricks that we've learned as to what is the part's natural position, or how do you design the CAD? Is it fully closed? Is it fully open? As you'll see here, it's partially open. So it makes a wonderful live hinge. Also, what's shown here is you see those two square arms, if you will, sticking out, and those will make sense here in a moment where we talk about heat staking. But a bit more on the application. Again, as I mentioned, it's outdoors. It is an aerospace application. So if you put those two things together, there is a product requirement called FOD. This product does have the potential to go into, let's say, a jet engine or some type of turbine engine. So again, being a polymer, being polypropylene helps us in this case as compared to some other filled materials, as well as definitely compared to metal. So it's a great fit so far, and those are two of the characteristics to start out with this picture. So Diane, if we go to the next one. The next slide, these are showing two components that are inside of that housing you just saw. So again, they're very small components. They would easily fit in your hands. We do have a couple dimensions on there for reference. If you can see, both parts are about 1 inch long. But what we're showing in the left-hand picture, the blue one, is you see the barbed fittings. So those were printed, very small detail. The Prodways machine was able to print those details and those features very nicely. So it's your basic bar press fit. And also that C-shaped feature you see, it has to flex to receive a round mating component. So we're using the flexibility of the PolyPro in this component. The right-hand component is a two-piece. You're actually looking at two pieces there. The blue is a U-shaped component, very small, that has to flex to get into two square holes that receive it. So that staple-looking component passes in there, and then we heat stake it on the outside. In other words, the opposite side of this part. So those are a couple slides of CAD models. That was the design intent. This program, Peridot, is also in charge of the product development and the design itself. So it's been fabulous to have design control, but also walk out and print the parts. So this is CAD, which always works in theoretical land. So then we move to the next slide of, let's take it from theory and let's move it into practice. And here's the physical components. Similar pictures. On the left-hand side, you'll see the red housing. The material's natural colors on the right, a translucent white, but showing here we did paint those, so that's another aspect. It can be painted, but you can see the live hinge there. And just to show that it's not photo opted, I do have to at least show it a little bit. So I got the same part in my hand, and it makes a wonderful live hinge. I've also got the natural unpainted material making a great hinge component. So that's what you're seeing on the left side. Right side, same components you just saw CAD of, the very small barbed fittings, the C-shaped component, and then the lower right is the staple. What we're finding is stability. So if these components were injection molded, the life or the memory of the material is pretty impeccable. PolyPro has proven itself time and time again. So was there some hesitancy using additive or a layering technology? Will it fatigue? With the testing that we've done to date, we've got great results. So that bonding of the sintering technology, that just the process is inherent to bonding those layers very nicely, and we're seeing that it performs right at the same threshold as injection molding. Now, you're looking at a design here. You may get a little bit of the gist of what we're trying to accomplish. We're evolving the design. These are a bit dated. Our latest design is, again, using the flexibility of the polypropylene material. We're preloading a component and using a spring force. So again, similar to what you see in the upper right corner is a C-shaped component. We've enhanced that. We've kind of thickened some walls, and we're using that basic shape, only a much thicker wall, and pressing the mating component into it, and it's preloaded. So it's going to spend its life preloaded until it's activated. So these are a couple pictures of the functional parts. So again, you're seeing a live hinge. You're seeing the ability to paint. We're heat staking it. Again, that's the lower right. The environment that this part will be in, it will be near some elevated temperatures, but it's also going to be ultraviolet, etc. And again, so far this program's been going 5 or 6 months, and to date our testing has been fantastic. So the ability to not only develop or design a product and print on the fly in the native production material has been invaluable. So that's a basic aerospace application. We'll come back and highlight some of those key points at the end. But Diane, if you go on to the next one. So we got a completely different application. Jeremy and Lee alluded to bottles or tanks. This is a basic bottle design. We redesigned it for demonstration purposes. So upper, lower with a cap. So again, it's a pretty straightforward design. The intent here is this part in production will be injection molded PolyPro. So we're going to print it. We're going to use the additive technology and make it in that same material. So we want to, as we alluded to earlier, use the same downstream processes that include welding. Next picture, please. So that we're going to take both halves, we're going to join them together. Here's the printed parts. Came out well. To give you a size scale, I've got it in hand. Let me measure it quick. This part is roughly 4 inches across, and it stands about 5 inches tall. You'll see the picture in the circle. It's kind of tough to make a weld joint look exciting, but there's our hot plate welded 2 halves that go together. We have subjected this one as well as a previous design, welded together. We put it under water pressure and then just put an airline into it. Took it up to about 20 to 22 PSI. The weld held great, and actually the upper and lower tank portions started to bulge a bit. So the weld seam was wonderful. We just may have to increase the wall thickness a bit. So it held, audience, may you have higher pressure applications, can we go above 22 PSI? We just haven't gone that far. We haven't burst one yet. But it was a proof of concept, proof of process, really, that we can hot plate weld these. Now, can you do other processes, spin welding and sonic welding? Yes. Again, it's polypropylene, so whatever you're doing in today's applications with this material, those different welding techniques should work just fine. The lower right, well, you see the cap. Whether you're in the bottle industry, or we're also finding a wonderful niche in caps and things like that. Again, injection molded, very high volume. Those are consumable items. We're starting to develop the relationship with the ability to print those. And as we touched on a little bit earlier, okay, so you're high volume, you're going to injection mold, but while that tooling's being made, the rest of the process can be set up. 3D print, necessary components. You want to work on your heat staking, your welding, your finishing, your painting, whatever downstream. While that injection mold tooling is being made, you can hand off to your manufacturing team true polypro parts, let them work on those other fixturing and downstream processes with native material parts. So that's been a real advantage for us. Yes, in that arena, it's prototyping, but manufacturing can be setting up and preparing while tooling is being made. So that dual path really saves a lot of time. So those are a couple of quick applications of how this material can be utilized. Diane, next slide, please. But really, the summary information that is shown here is what it's about. So to our tank assembly, we were able to prototype in the same material as production. And I know we already touched on it once, but I can't stress that enough, that as you product designers and even the marketing community out there, again, I'm very familiar. We have machines here that use the photopolymer technology. When you have to say it's kind of like your production material, we have to cut some corners and make some assumptions. In this case, it is the exact same material as production when it's polypro. This tank project specifically, additive is all about saving time, and additive is all about saving cost. So to give you a reference, what did we gain here? These bottles are often made, they have to be in the native material, so they're injection molded, even if you only want 10, 20, 50 pieces. And you can imagine what those tools can cost. In this particular case, it's just shy of a $20,000 tool that would have been needed to make just 20 pieces. That's not counting any design iterations and tooling modifications, and roughly 6 weeks. So round numbers, $20,000 in 6 weeks saved just by printing these components out of this polypropylene material. And again, we were able to provide, it provides the ability to weld components. We hot plate welded it together. Not only Peridot, but our customer put it through pressure testing. The chemical compatibility, same as production polypro. So that's applicable to whatever your injection mold grade will be. But we have highlighted there for this tank assembly, fully functional. When you can hand off a component to an engineer or a rapid situation where they're trying to go to speed, go to market quickly, this is fully functional. Don't have to make any exceptions. Hey, it'll work, but don't put it under temperature. Hey, it'll work, but don't do this to it. It's really reassuring when you can confirm with the customer that it's fully functional. And not only that, but this particular application, are you going to use additive in, let's say, automotive, make thousands and thousands? No, probably not. So it's in the prototyping arena in that field. But in other situations where bottles are needed in lower volume, you know, whether it be off-highway applications, whether it be equipment that is built in lower volume, this is a wonderful process and a wonderful material to actually use them in production. You know, whether it be aerospace, whether it be, like I said, off-highway, large equipment, you can make the bottles on the fly and they're actually production components. So as we shift over to the right-hand side, the aerospace application, again, similar bullet points. The prototypes are made in the same material. Now, in this case, we're planning to do production of this component also on this technology. So we can prototype in the same material and the same process as we're intending for production. So back to our poll question, where 55% of you have considered or have done a transition from conventional to additive for your production, and 20% of you said, no, I haven't done that yet. You know, I know we all read our information in the magazines, we hear through the grapevine, what's additive, how cost effective is it getting? I really think this material is a quantum leap in offering the product audience, the product arena, look, you can use additive now in a cost-effective material with a great refresh rate and produce production components. I highlighted the live hinge ability, again, right off of a 3D print. The snap fits and the barb fittings, we're using it in this application. And the heat staking, the coloring, I do have to say, you see the red that we painted. We've done a dye process. This color's black, and just hot off the presses, we just received a component that's been metal coated. So we've painted, we've colored, we've even applied metal to it. It's a wonderful material. So again, that's the surface finish options. It does have nice thermal resistance. And again, I gotta highlight, fully functional. So in this case, to try and put some savings to it, it enables manufacturing, again, with no tooling. In this case, the design that you see on the screen, that's just shy of a $30,000 tool and at least 10 weeks to make that tool. So trying to quantify what it is we can produce, we're saving those kind of dollars and that kind of time. So there's a couple applications among many, many, but starkly different, but we're using various positive aspects of this material to make functional parts. Anything you guys want to add to that? Anything I glossed over? But so far, so good. We love the material. It runs consistent, reliably.
No, I think that's great.
Yeah, I think you did a bang up job, Dave.
Yep.
I just to like bring it around, right? Just these ideas of you know, functional parts and prototyping all in the same run. So being able, that's I've only been in the industry since 2014, but that's always been like the holy grail, right? Of being able to prototype and then prototype in your production material, and then the next step, which you know, not that long ago we weren't even thinking about, which was being able to do production in additive. And that's so that's an exciting piece of the puzzle. You know, just to kind of add a little bit to what you said, Dave, like just this one tank assembly, great application for you know, for engine manufacturers, for marine manufacturers, all of these, even recreational vehicles, right? Anyone where you've got 5,000 pieces or 5,000 units a year or less, it allows you to open up customization options that you just didn't have before. So I think it's great. I'm really looking forward to watching both of these applications as they continue to unfold, especially the aerospace one. That one,
right?
That's going to be neat.
We're excited about it too, and yes, when it's done, we'll be a bit more boisterous about it. But right now, we got to be a bit limited. But
yeah, no, I understand.
I know Diane's keeping us on a clock, but to expand on design for additive, I know that's actually, we work with some academia, and that's being taught in our universities, and it's starting to infiltrate into product design. It's one thing to use additive for niche applications. You know, I'm sure we all know about the hearing aids and the dental and things like that, which is great. But to now have a material that's versatile and robust enough to go into, I'm going to say, a bit more broad or commercial applications. You can print. Obviously, I think we would all know that you can do things with geometry that you can't do in molding. You start combining components and making it easier to assemble. So just the whole additive discussion really comes to fruition when you have a material like this that is common as acceptable as polypropylene.
Exactly.
That's cool.
So Diane, I think you said there's a few questions that have come through. I guess we can.
Yes, there are quite a few questions that have come through, and we've got some time to go through a few of them. Just a reminder, if we don't get to them today, we will follow up with you directly in the next couple of days. But one of the questions that came in is, what is the cost of each prototype discussed today?
Good question. Relatively speaking, at least, and this is an opinion in a company of one, but relatively speaking, this process, this material, so SLS with polypropylene material, is oftentimes a lower cost than the photopolymer or SLA, and it's similar or slightly more than the filament technology. But to give you a reference, actually, we've printed so many iterations of this component. It runs approximately $300 to $500 a piece. And again, what you're seeing in the picture in red is half. If you can imagine another component just like that, it makes a spherical-like component. And the tank that you see in the picture, since that was an internal development with the customer, to be honest with you, I don't have the pricing right off the top of my head, but going for scale, this would again probably be a $400 part roughly. Now again, keep in mind that when you're making 1s and 2s and even 5s for prototyping is one thing, but this material offers a cost effectiveness when you do it in scale, and this is all relative to additive. Scale might be a 100 pieces. The price is dramatically different because just like other processes, you start amortizing setups, you start amortizing some of your fixed costs, and the price comes down considerably. So those numbers I throw out are for low volume prototypes.
Great, thank you. Let's see, we've got a lot about the material. Here's one. Does polypropylene 1200, PP 1200, give off any gas when pressurized air is put through it?
Diane, if you could clarify that, does it allow air to pass through?
Does it give off any gas when pressurized air is put through it is the question.
It sounds like maybe an outgassing question as well. I'm not totally sure on what the driver is there. You know, some of those the outgassing data, things like that, should be available through Prodways. Their material spec folks will be able to answer the off-gassing questions. As far as the maybe now that I think about the question, Dave, do you think it has more to do with like is it, you know, it's air tightness? And if that was an early question, maybe that was before we talked about you know, your pressure testing that was done, because you said you pushed it up north of 25 or 30 psi.
North of, we were in the low 20s. That's what
Okay.
I wanted to do. If this is a situation, medical or aerospace, where outgassing is a question, I'm going to defer to Prodways and a little bit deeper, pulling back the layers to understand the outgassing. So I can't speak to that. But if it's a question of, is it a porous wall, or is it the ability to hold, is it a solid wall that can hold water or hold air? Yes, that I can confirm. That's definitely, it produces a part. And we're not impregnating these. You know, I know it's common to use CA and things like that. This, let's call it 22 PSI that we subjected it to right out of the machine. No surface prep.
Great, okay, thank you. We've got one here, and it is, what are the breakout procedures? Do you need breakout while still warm or complete cool down?
I'll go first on this one, but these guys can say what you're supposed to do. No, we let it cool down. We've established an internal process that it seems to be working quite well. So we leave it in the machine, let it cool down to a given temperature. That's oftentimes a rough rule of thumb. The cool down in the machine is the same amount of time that it took for the build. You got a 2-hour build, you leave it in there about 2 hours. But we've established a magic temperature that we'll pull it out a bit warm. Then we continue to leave it in the cake until it reaches the next temperature. At that point, we're free to break it out. We have a breakout station and sift the material, etc. So again, once build completes, the machine has its own cool down. Then we put thermometers in it. We allow the cake to stay in the machine until it reaches X temperature. We bring it out, let the cake sit on the table until it reaches Y temperature, and then we begin breakout. So to expand that a bit, just processing in general, what did we do to prepare for this technology? It runs very nicely. you're dealing with a powder. So again, those of you listening that are used to the filament technology or the photopolymer, they are inherent to their needs, but you're dealing with a very fine powder. So our breakout area, if you will, our blasting area, we have a separate room to keep all that residual powder in one area and an air cleaning system. But other than that, those types of requirements that come with any powder, the cool down, the warping, I know some of you may be experienced in the SLS technology. We're not having significant warping issues, so it is pretty robust in that regard.
Can you share, Dave, what the time is like? So after a build, is it sitting for 2 hours, 12 hours? What are those generally? What's that timing like?
Well, the machine is fast, and given the build envelope, Lee, correct me, I believe it's 300 millimeter cubed. So rarely does a part go into the morning. You know, we typically start them midday. They go into the night. It's got its own cool down. When we come into the morning, it's pretty much ready to take out of the machine. Yes, it's build dependent, but that's typical.
Right.
But if it's a 6-hour build, it usually takes about 6 hours to get to the take out of the machine temperature.
Okay.
And then we're letting it sit on the cart for another half of that. So maybe about another 3 hours. Are there techniques that can be done to get it out of the machine faster? There sure is. You just put it in a warm box, let the cake cool down in a separate cooling box, if you will. So there's opportunities to free the machine up quicker for more turnover.
But you are able still to cycle, like you're able to do a full build cycle in under 24 hours, and it's not.
Oh, yeah.
You don't have people coming in at 3 o'clock in the morning or crazy stuff like that.
No. In fact, we've got a small component. We just received another customer order that when we're done with, we will have produced over 9,000 pieces on the machine. So that build, we've got like clockwork now. We start in the morning, it's done. We shut everything down. You come in the morning, it's done. Can we cycle it twice in a day? Yes, we can, but we put a lot of this little part in each build. So no, we're cycling easily every business day.
Good.
Yeah, and Dave, sounds like you're doing it the way that we recommended anyway. So
Right.
Yeah.
I was more interested in what Dave said anyway. What we're supposed to do.
We've tried a lot of things. We have pulled them out too early, let me tell you.
Yeah.
Oh, for sure.
We've got time for a couple more. Here's one that I noticed the parts seem a little coarse with this material. Process in some of the automated finishing stations on the market. With this process in some of the automated finishing stations on the market, considering the PP natural chemical resistance.
Good question, and
Yeah.
we're being completely honest, whether we should or shouldn't be. This red part, you saw close-up pictures of it. Did you see some layer lines? You sure did. We did not touch this part because we're still in development of this part. We're not spending a lot of time benching it. In fact, the pictures you saw in the presentation had no post-processing to it. Layer thickness, 4/1000 of an inch, right, Lee? I gotta think. But so just like any additive process, yes, you're gonna have some layering, some stair stepping. And again, are we showing you worst case scenario? It's a cylindrical part that I built laying flat, so it's gonna be almost worst case scenario. If I built that cylinder standing up, you probably wouldn't see that. So yes, it is a powder material. It's gonna be a bit grainy, but I would remind you that this part was finished with a metal coating, and I don't know if you can see it, but it's extremely smooth. Yes, it did take some post-processing. So, and the person's asking about some of the post-processing equipment out there on the market. We're not using it. I'm aware of it. We're looking into it. But right now we're using a blasting technique, elbow grease, and things of that nature to smooth out our parts.
I can speak to the chemical, the chemical post-processing has been pretty roundly ineffective on polypropylene, which I don't think anybody's going to be surprised by, right? Because of its chemical resistance. I do know that a couple of the major players are working on formulations that will etch and smooth the polypropylene. So I believe that's something that's coming. But right now, I don't know that we have a lot that we know of to be able to do that chemically.
Yeah, I'm sure you guys have sent out parts just the same as we have to these companies, and yeah, It's been relatively ineffective up until this point, but as I understand, there is progress being made.
Yep.
Okay, we've got time for one final question. It's kind of a double question. How about the grain size and porosity of PP 1200 on high pressure applications, and is it biodegradable?
So I'll take the to my knowledge, it is not biodegradable. I can take that one. the big question I'll throw over the fence.
Yeah, grain size. I don't have that in front of me right now. I can definitely get back to you on that.
Perfect.
As far as
yes.
there was a porosity component to that question as well, right?
There was. It was. Let me go back up to that question.
Right, good point, Jeremy. And
Porosity on high pressure applications.
Right.
And I don't want to ask a question with a question, but define high pressure. So I know hopefully we have an audience that's very diverse and they're coming from lots of different applications. So that's going to be application specific. I spoke to low 20s PSI, but to porosity in general or not sintering, we've definitely not seen that. So I can speak from a processor standpoint. That's definitely not been a problem. We've built a few thick-walled parts, and now you're getting into the Prodways technology has different settings for different part geometries. If you've got a thick-walled part, if you have a thin-walled part, well, that's now in the software settings that it has performed well. So I guess if the question is, are we seeing porous walls? We're not. So that's how I would understand that question.
Right.
Perfect. Well, we had other questions come in, but we are out of time for today. So I'd like to thank Lee and Dave and Jeremy for being fabulous panelists on this webinar. And if you did submit a question, as we said, we will follow up with you directly if we did not get to it in the next couple of days. And we thank you for joining us today. We know your time is valuable. We appreciate your participation. If you have any questions or want more information, you can certainly contact us by visiting our website, which is prodways.com. And we want to thank everyone for attending and enjoy the rest of your day.
Thanks, everybody.
Thank you.
Yes, thank you for attending.